I'm reading a chapter of the book by Somalin, The Search for What Lies Beyond the Quantum, Einstein's Unfinished Revolution. This chapter is about a magical realism that's about the parallel universe. Okay. We saw in the last few chapters that there are options for realists, but notice that they all require changing the theory. The spontaneous collapse models make the sudden collapse of the wave function part of the dynamics of the theory. The collapse occurs whether or not measurements take place, and without regard to what we know. The resulting theories disagree with quantum mechanics generally, but preserve a domain of agreement sufficient for them not to contradict the results of experiments done so far. Pilot wave theory is another option for realists. Rule 2 is suspended, so the wave function evolves always according to Rule 1. But a new element is added, particles, whose travel is guided by the wave function. So this theory is also different from quantum mechanics. When the particles are in quantum equilibrium, the predictions of the two theories overlap. But after the quantum equilibrium, the predictions of a pilot wave theory differ from those of quantum mechanics. It should be wonderful if someday experiments confirm that nature favors one of these realistic theories over quantum mechanics. But suppose it turns out that after many years, or indeed centuries, we have no experimental results which require a modification or completion of quantum mechanics. In particular, what if no limit is found to how large or complex a system can be and still be put in a superposition? Suppose, in other words, that quantum mechanics in its original form appears to be completely correct. Would there be any options for realists? The reason it is hard to be a realist and believe in quantum mechanics is Rule 2, which gives a special role to measurement. The suddenness of the collapse of the wave function on measurement dictated by Rule 2 means quantum states change in time in a way that pays no heed to locality or energy, and instead seem to depend on what we know or believe. Since it makes the quantum state beyond on our knowledge, this cannot be part of a realist theory. Such a theory could not have a Rule 2 among its postulates, because that would contradict realism. So we would have to build our theory on Rule 1 alone. This is also a modification of the theory, but it is one it shares with a pilot wave theory. So perhaps it is a change worth exploring. Such a theory has no obvious reference to experiment, also no apparent notion of uncertainty or probability. Because Rule 1 is deterministic and makes no reference to probability, can we possibly make such a theory work and stay consistent with realism? One way to accomplish this would be to derive Rule 2 from a theory that doesn't postulate it. The collapse of the wave function would happen only in certain special circumstances, such as when an atom interacts with a large human-sized measurement instrument. To do this, we have to find the rules for uncertainty and probability arising in a world described by a theory that has none. The project to make sense of quantum mechanics, based solely on Rule 1 and in a way that is consistent with realism, has a long history. It was initiated in 1957 by a PhD student of John Wheeler's named Hugh Everett III, and so can be called Everettian quantum mechanics. But it is most often referred to as the many worlds interpretation of quantum mechanics, because some have argued, not without controversy, that it implies that the world we experience is just one of a vast number of parallel universes. Everett's proposal was presented in his PhD thesis of 1957 and was published the same year. It was unusually short for a PhD thesis, yet it was to have, after a while, a big impact. Everett, as many have, left academic science just after his PhD to begin a career in the defense industry, so his thesis was his only contribution to physics, and it took many years before it was widely read. But apart from de Broglie's thesis, I can think of no other PhD thesis which was to have, over the long term, such a disruptive or revolutionary effect on the foundations of physics. One of Everett's ideas is certainly correct and useful. If there is no Rule 2, wave functions don't collapse. So we have to describe what happens in a measurement using only Rule 1. As we saw in our discussion of Schrödinger's cat at the end of Chapter 4, interactions, including measurements, lead to correlated states. The example we discussed was in between equals to excited and no and alive, or ground and yes and dead. The O signifies a superposition of different possible situations, in each one of which the atom, Geiger counter, and the cat are all correlated, given that they are in a superposition of states. Observables such as the aliveness of the cat have no definitive value. But Everett noticed that nevertheless, we can read this superposed state as giving us two contingent statements about the state of the combined system after the measurement. These contingent statements are: number one, if the atom is in an excited state, then the counter will read no and the cat will be alive. And second, if the atom is in the ground state, then the counter will read yes and the cat will be dead. This tells us that the atom, the counter, and the cat have become correlated by the photon's possible passage through the detector. The superposed state doesn't tell us which outcome will be observed, but it tells us that the outcome expresses a correlation between the state of the atom and the states of the counter and the cat. This much of Everett's thesis is unimpeachable. It is generally true that interactions between two quantum systems set up correlation between the states of the two systems, and these correlations can be read as sets of contingent statements. This is a consequence of Rule 1 applied to interactions. But notice that this doesn't do. It doesn't tell us which outcome will be observed. Contingent statements may be useful as they give us definite information about the system, but they do not give us complete information. A theory that gives us only contingent statements could not be enough for a realist. So Everett went further. To make the theory with only rule 1 realist, he proposed to change our conception of reality. Everett suggested that a state which consists of a superposition of states of detectors describes a reality in which both outcomes happen. In this enlarged reality, both contingent statements will be true. That is, Everett asserted that a full description of reality is the superposition of the two states. But only part of what that implies is that the following statement is true. Quote, "The atom is in the excited state. The counter is no, and the kite is alive. And the atom is in the ground state. The counter reads yes, and the kite is dead." This should seem to be blatantly false. In the world we live in, the kite experiences only one outcome. This is why in Chapter 3 we described the superposition as characterizing O. Either she experiences that she is alive, or she's dead and experiences nothing. In our world, it is one or the other. Everett proposed that the world we experience is only a part of the full reality. In the enlarged world which he proposed makes up that full reality, versions of ourselves exist that experience every possible outcome of every quantum experiment. In other words, the O of ordinary experience becomes, in quantum mechanics, an end. We say the cat is alive or the cat is dead because the two states are mutually exclusive. But in this affirmation, it can nevertheless be true that the cat is alive and the cat is dead. The idea is that each time an experiment is performed, which could have different outcomes, the universe splits into different parallel worlds, one for each of the possible outcomes. We split as well, along with the world. The experiment creates an additional version of ourselves for each of the possible outcomes. Each version of ourselves lives from then on in a world described consistently by one of the contingent statements we can read of the combined state. In contrast with the pilot wave theory, Everettian quantum mechanics has no particles, so nothing distinguishes the different branches from each other. We then are invited to regard all branches as equally real and work out the consequences. So if Everett is right, I'm at this moment in Toronto, and I'm in London, and indeed simultaneously in married place my life might have taken me, including the ocean floor of Peggy's Cove. These branches are sometimes called worlds. You can see why Everett's proposal has come to be called the many worlds interpretation of quantum mechanics. For this to work, each version of an observer must have no way to communicate with the others. The branches must be autonomous. What I have described so far was Everett's initial version of the many worlds interpretation. On examination, it turned out to be a bit naive, as it ran into several big problems. The first problem with Avery's formulation is that he suggested that the branching happens when a measurement is made, but this makes measurement appear to be special, whereas it is a basic tenet of realism that measurement are ordinary interactions to be treated like any other. Indeed, Rule 1 makes no distinction for experiments, so if you are a realist, you must insist that what happens for a measurement must happen more generally. The key thing that causes a splitting is an interaction, which produces a correlation between the systems that interacted. These correlations can, as we saw, be expressed as contingent statements describing different possible outcomes of that interaction. To avoid making experiments special, the universe must split each and every time there is an interaction which has more than one possible outcome. But this is happening literally all the time. All that is required is for two atoms to collide with each other, and that is happening myriad times a second just in the air in this room. Moreover, the interaction that causes the splitting can happen anywhere in the universe. So while you are reading this sentence, you are splitting a vast number of times into a vast number of versions of yourself. This is a lot to ask someone to believe, all in the name of realism. No wonder it took some time for Avery's ideas to catch on. A second problem is that if the branching is to replace Rule 2, then it must be irreversible. To reproduce the basic fact that we observers experience every experiment to have a definite outcome. Indeed, the action of Rule 2, which the branching is supposed to replace, is irreversible. But the branching is supposed by average to be a consequence only of Rule 2, which is reversible. A third big problem is giving up Rule 2 has to do with probabilities, or rather, their absence. Experiments measure probabilities for different outcomes to occur, and comparing these to the predictions of the theory is an important part of testing quantum mechanics. But notice something important. Rule 1 doesn't speak of probabilities. All reference to probabilities in quantum mechanics comes from Rule 2, which gave us a formula for how probable each possible outcome is. The formula, as we noted before, is called Born's rule, and it relates probabilities to the square of the wave function. This is the only part of a quantum theory that refers to probabilities, and it is part of Rule 2. If we eliminate Rule 2 from quantum theory, we have nothing left in the theory that speaks of probabilities. As a result, Avery's version of quantum mechanics tells us only that every possible outcome occurs, not with some probability, but with a certainty. That is, for every possible outcome of an experiment, the many worlds interpretation asserts there is a branch in which it occurs. There is no sense in which some branches are more probable than other branches. All Rule 1 can assert is that with a certainty, all branches will exist. So we seem to have lost an important part of quantum mechanics. That part which predicts the probabilities that different outcomes occur. Everett was not dumb. He was aware of this issue, and he attempted to address it. In his thesis, he offered a way to predict probabilities using only Rule 1. To accomplish this, he suggested a way to derive the relation between probabilities and the squares of the wave function, a relation which Rule 2 postulates directly from Rule 1 alone. At first, many were impressed by this result. I know I certainly was when I first read Everett's paper, but it turns out something was concealed in his derivation. Like many erroneous proofs, the argument assumed what was to be proved. The relation between the square of the wave function and the probability was snuck into a seemingly innocuous step, which assumed that branches with small wave functions have small probabilities. But that was tantamount to assuming a relation between the size of the wave function and probabilities, and so the proof proved less than was first claimed for it. Everett's proof did establish one important thing, that if one wanted to introduce quantities called probabilities, it would be consistent to assume they follow Born's rule. But it did not prove that it was necessary to introduce probabilities, nor did it prove that those probabilities must be related to the size of the wave function. Yet another problem with Everett's original formulation of the many worlds interpretation was that splitting the quantum state into branches is ambiguous. As I explained, each branch is defined by some quantity having a definite value. There is one branch in which the atom is excited and the cat is alive, and another branch in which the atom is in the ground state and the cat is dead. But why these and not some other quantities? Ground and excited are states of different energy. But there are other incompatible quantities that we might use instead to define a split. There will be some superposition of ground and excited states that corresponds to the electron being on the left side of the atom, and a different superposition that corresponds to the electron being on the right side. Let's call these states left and right. Why not split each with respect to these? These would lead to states of the cat, which were superpositions of alive and dead. She no longer would experience a world where there are definite outcomes to experiments. But Rule 1 doesn't care whether she experienced definite outcomes or does not. We call this the preferred splitting problem. At first, there seems to be an obvious answer to the preferred splitting problem. We must split the wave function so that the different branches describe situations in which microscopic observers, like the cat, see definite outcomes. But this is tantamount to introducing Rule 2, because it gives what microscopic observers see a special role. You have not solved the mystery of why microscopic observers see definite outcomes. And by giving observers a special role, you give up on achieving a realistic interpretation, which must be based on hypotheses about what is real in the absence of observers. That's the end of chapter 10.